Alright, hello everybody. So today we're gonna do our last lesson in limits. I'm going to try to upload more from now on. I'm gonna try to finish this entire Calculus 12 course maximum over the next month. And then I have some new university level math courses that I'm gonna try and upload because people are going to university and they're going to be nervous about the math. Maybe by some preparation they're going to be more successful. So today we're going to solve some questions on continuity, and I also have a thinking problem at the end so that you guys see what that's like. Okay, let's just get to it. Find values of a and b so that f of x is continuous everywhere. And f of x here is what's known as a piecewise function. Why is it called that? Because during different pieces of its domain, it has different algebraic expressions. So for example, if x is less than 2, then the algebraic expression associated with the function is x squared minus 4 over x minus 2. If x is between 2 and 3, then the middle one. If x is larger than 3, then the bottom one, right? So that's what we call a piecewise function. Now, there are multiple things for you guys to remember. Number one is the condition of continuity. So this is what needs to happen for a function to be continuous. At, let's say, x equal a. Well, for continuity to actually happen, the limit of your function as x approaches a minus, so as x approaches a from the left side, should be equal to the limit of f of x as x approaches a plus, so this is approaching a from the right side, and this needs to be equal to the value of the function at point a. So if this holds, then your function is continuous at x equal a. Now, the major problem is this doesn't really solve anything for you here. Why? Because according to the question, this needs to be continuous everywhere. Everywhere is an infinite number of points. So we can't really apply this condition of continuity to every single point that is in R. There's infinite points. We have to do this infinite times. It's not possible. However, it becomes possible when we realize a very important point, and that is most of our functions that we have dealt with, you have dealt with as a grade 12 advanced function student, basically. Most of those functions are all continuous all over their domain. So most, I'll put it in quotations. So most normal functions you've seen so far are continuous all over their domain. So examples of these are polynomials, for example. Rational functions. So I'll add one small note on this one. So in rational functions, it looks like there's a discontinuity. So rational functions in general are not continuous. The only thing is, at the point where they're not continuous, that point is not in the domain. So the only point where they're not continuous is their vertical asymptote. And vertical asymptote is not really in the domain of the rational function. So rational functions all over their domain are continuous. They're just not continuous at their vertical asymptote, which is not a part of their domain. So polynomials, rational functions, root functions. So square root of x, cubic root of x, etc. Exponential functions. So things like e to the power of x, 2 to the power of x, 2 to the power of x minus 2, these are all continuous. Logarithmic functions, they also have the same note as rational functions, right? They have asymptotes, but the asymptotes are not a part of their domain. Sine and cosines, and etc. So most of these functions that you've dealt with over your high school education, these are continuous. So what that means for us here is that to check for continuity everywhere, the only places we really need to check are these places where the algebraic expression of the function changes. So, for example, in our function, the places that the function has a sudden change of expression is at x equal 2 and at x equal 3. Right? At x equal 2, it jumps from the first to the second. At x equal 3, it jumps from the second to the third. Everywhere else, it's continuous because these are just, this one is a linear function, this one is a polynomial, both are polynomials, and then this one is a rational function, and it's before its vertical asymptote, so of course it's going to be continuous. So all I need to do is I need to prove that it's continuous at x equal 2, and it's continuous at x equal 3. So I'm going to do that. So this is for x equal 2 first. We're going to do the limit of f of x as x approaches to minus. Well, what is that going to be equal to? Well, these are values of x that are less than 2. So I'm going to choose the top one. So it would be the limit of x squared minus 4 over x minus 2 as x approaches to minus. And this would give you, well, if you plug in the 2, you get a 0 over 0. Luckily, if you watched the previous video, you've seen that we can deal with indeterminate forms by factoring them, right? So I'm gonna factor this one out. The top is a very easy difference of squares. I can write this as x minus 2, x plus 2, and then all of that over x minus 2, which gets rid of the trouble child x minus 2 right there. And I can just plug this 2 in, so it becomes 4, because it's 2 plus 2. Perfect. And then I'm also going to do the same exact thing, just this time for the limit of f of x as x approaches to plus. So this would be equal to, so x approaching 2 plus are values of x that are very close to 2, they're just slightly larger, right? That's basically the same, the second interval, right? Values that are close to 2 but after 2. They would definitely be between 2 and 3. So we're going to use the second one. So it would be the limit of ax squared minus bx plus 3 as x approaches 2 plus. And hey, look at that. For this one, I don't have to deal with an indeterminate form or anything. I can just plug it in. I can just plug the 2 in. So it is 4a minus 2b plus 3. As an added bonus, this is also the same thing as f of 2. Because when x is equal to 2, you're still on the second expression. So if you just plug in 2 in there, you get the same thing as this. So I don't actually have to do like a third time. Now, I just have to put these equal to each other. So that means 4 is equal to 4a minus 2b plus 3. Which leaves you with 4a minus 2b is just equal to 1. That's our first equation. Now, I want a and b, and I only have one equation. That's not good enough. I'm going to need a second equation. Where do I get that from? Well, I'm just going to apply that condition of continuity. It's just this time I'm going to apply it to x equal to 3. So it's the limit of f of x as x approaches 3 minus. That would be equal to, well, these are values that are very close to 3, but still less than 3. That means I'm going to use the second one. So it would be the limit as x approaches 3 minus of ax squared minus bx plus 3. And again, I'm going to plug it in. Nothing disastrous is going to happen. So 3 squared is 9, 9a minus 3b plus 3. And then now I have to do the same thing for 3 plus. So I'll do the limit of f of x as x approaches 3 plus. Now for that one, I have to use the bottom expression because these are values of x that are larger than 3. So it would be the limit of 2x minus a minus b as x approaches 3 plus. I'm just going to plug it in. Becomes 6 minus a minus b. And again, as an added bonus, this is also equal to f of 3. Because when x is equal to 3, you have to use the bottom expression. And then from here, you just have these two have to be equal to each other. So it's 9a minus 3b plus 3 is equal to 6 minus a minus b. And if you simplify this a bit, you get it is 10a minus 2b is equal to 3. That's our second equation. Now, 2 equations, 2 unknowns, something that you should be able to solve very rapidly. So here I can see that I have a minus 2b here and a minus 2b here. So the easiest way to get rid of these two is just by elimination, right? I'm just going to minus the 2 equations from each other. So I get 10a minus 4a, that's a 6a, minus 2b minus 2b, they cancel each other out, and then 3 minus 1 is just 2. So I get a is 2 over 6, which is the same as 1 over 3. How do I get b? Plug it into either of the equations that you like. I'm going to plug it into 1. So I get 4 times 1 over 3 minus 2 times b is equal to 1. Which means minus 2b is equal to minus 1 over 3. This is a 4 over 3, goes to the other side. 1 minus 4 over 3 is negative 1 over 3. That means b is just equal to 1 over 6. So, major things to note. Number 1, functions that you know of, functions that you've worked with, most of them are continuous everywhere. So the only places you have to check for continuity are at the breakpoints of your piecewise function. And then you just have to know what it means for a function to be continuous, which is the condition of continuity. Just apply that to each of the breakpoints, and we're good. Okay. Now this second one is an example of a thinking problem. You should expect one of these on, at least one of them on every one of your tests. It says if the limit of that atrocity as x approaches negative 3 is 6, find the values of a and b. Well, the first thing you should note, as always with finding a limit, is if I plug this negative 3 in here, the top of that fraction is going to become 0, because x plus 3 is going to be 0. Now, if the bottom of the fraction does not become 0 when I plug in negative 3, then I am going to have 0 up top divided by a whole number at the bottom. That can never be equal to 6, because 0 divided by anything is just 0. So for this to happen, for this entire limit to be equal to 6, you would need to have a 0 over 0, which is then an indeterminate form, which then you can do math on and then possibly turn it into 6. So that's the first realization, is that when I plug in negative 3 into the top, I get 0. That means the bottom also has to be 0. Otherwise, this limit is never going to be equal to 6. So since plugging in x equal to negative 3 into the numerator gives 0, in order to have a non-zero limit, as we do here, we have a non-zero limit, 6. the denominator needs to be 0 as well. So that then we have an indeterminate form, and then simplify it, and then possibly get 6. So let's plug it in. So we get square root of a times minus 3 squared minus 2 minus 4. This should be equal to 0. And that already gives you a equation for a that you can solve. So this gives you the square root of 9a minus 2 is equal to 4. And that means 9a minus 2, I can just square both sides, is equal to 16. So 9a is 18. So a is just equal to 2. Very good. Now, we have the limit as x approaches negative 3 of x plus 3 to x plus b over the square root of ax squared minus 2 minus 4. Or actually, we already know a, so we can just replace this a with what it actually is, and that is 2. So now we set it up in a way that this limit is going to be 0 over 0. So it's an indeterminate form. How do I deal with it? There's a root at the bottom. As we discussed, the roots are very easy to deal with in indeterminate forms. You just multiply both top and bottom by the conjugate. So what would be the conjugate here? Same terms, just the sign between them turned into positive. So it's square root of 2x squared minus 2 plus 4. And the top needs to be multiplied by the same thing. Otherwise your entire fraction changes, and that's not good. Now the bottom is a minus b times a plus b example. So we can just do difference of squares. So it would be the first one squared, which gets rid of the root, minus the second one squared, which is just 4 squared, which is 16. And up top, you just have all that trash. So x plus 3, 2x plus b, and then square root of 2x squared minus 2 plus 4. Now, this is at the bottom. This is 2x squared minus 2 minus 16. So that's 2x squared minus 18. So one thing we can do immediately is we can get rid of, or factorize it too rather. We can't really get rid of it, but we can factorize it too. So it becomes x squared minus 9. And x plus 3, 2x plus b, square root of 2x squared minus 2 plus 4. And hey, take a look at that. We kind of made a factor of x plus 3 happen at the bottom, because this x squared minus 9, if you just do one difference of squares on it, it is 2 times x squared minus 9. So it is x minus 3, because it's x squared minus 3 squared, times x plus 3. And up top you have x plus 3, 2x plus b, and then square root of 2x squared minus 2 plus 4. And then x plus 3 and x plus 3 get trashed, which is what we wanted. We don't want a 0 over 0. So I'm going to plug in negative 3 now. It would be negative 6 plus b, because 2 times negative 3 is negative 6. And then square root of 2 times negative 3 squared, that's 2 times 9, that's 18. 18 minus 2, that's 4. Or sorry, 18 minus 2, that's 16, and then root of 16 is 4, and then 4 plus 4 is just 8. Lots of calculation in my head, you can just plug it in the calculator. And then 2 times minus 3 minus 3, that's minus 6. And what was this supposed to be equal to? The limit needed to be equal to 6. And hey, look at that. This gave you a equation for b. So you get minus 6 plus b. You can simplify the 8 and the 2, so that leaves you with a 4. You can simplify the 4 and the 6, so that leaves you with a 2. So it's negative 6 plus b times 2, and then multiply this in is negative 3 times 6, which is negative 18. So negative 6 plus b is negative 9, basically dividing both sides by 2, which means b is equal to negative 3. Half of this question was not a thinking question. So the part where I just multiplied both top and bottom by a conjugate and simplified, that's an application problem. The only thinking part of this was that you had to understand that in order for 0 over something to be equal to 6, the bottom also needs to be 0. That's the thinking aspect of this question. Okay, that basically finishes the limit unit. We're gonna start derivatives next time. And that's going to be uploaded very soon. It's going to be uploaded probably tomorrow or the day after that. And yeah, I'm going to try to speed the upload of these videos. So please like and subscribe. Tell your friends about it if anyone needs calculus help. And I've linked a Discord and my Instagram on my About page. And I'll also try to include them in the comments. If you had any questions, you can just come onto the Discord server. That Discord server is designed for answering problems. And I'll be happy to help. Have a good night.